Hello, welcome to the second unit, matrix eigenvalue problem and quadratic forms. In this lecture, we are going to see how to orthogonal and diagonalization of symmetric matrices. That is, orthogonal diagonalization of symmetric matrices. So we'll deal this topic by taking a problem here. So the question is here. Find an orthogonal matrix that will diagonalize the real symmetric matrix A equals to 1, 2, 3, 2, 4, 6, 3, 6, 9, and also find the resulting diagonal matrix. So here he is asking the orthogonal diagonalization of the symmetric matrix. So clearly it's a symmetric matrix. So the procedure is simple. So the first step involved in this is you have to get the eigenvalues for the given matrix. Then for the corresponding eigenvalues, you have to get the corresponding eigenvectors. Once you got the eigenvectors, then check whether the eigenvectors are orthogonal or not, pairwise orthogonal or not. If they are pairwise orthogonal, then form the model matrix P. Here it is not the ordinary model matrix, it is a normalized model matrix you have to construct. Once it is done, then the same procedure you have to calculate P inverse, right? And you have to show that it is nothing but D. Now that is the simple procedure. Now we'll see this step by step. So this is the given matrix A 1 2 3 2 4 6 3 6 9. Clearly it is a symmetric matrix. So first I am calculating the characteristic equation. So the formula is at A minus lambda I equals to 0. So using this formula, we calculated and we got the roots is lambda equals to 0, 0, 14. 0, 0, 14. So repeated eigenvalues we got. Now consider the system 1 minus lambda 2, 3, 2, 4 minus lambda 6, 3, 6, 9 minus lambda x, y, z 0, 0, 0. So this is the system. Now I am going to calculate the eigenvector corresponding to the eigenvalue lambda equals to 0. Put lambda equals to 0 in this system 1. So if you put lambda equals to 0 here, what you will get is 1, 2, 3, 2, 4, 6, 3, 6, 9, x, y, z 0, 0, 0. Now reduce this matrix to upper triangular matrix. So to reduce that one, we applied this row transformation. So R2 minus 2 times of R1 and R3 minus 3 times of R1. So if you do that one, you will get this matrix. From this, I can write x plus 2y plus 3z equals to 0. Now I have to choose arbitrarily y and z. So I selected my z is k1 and y is k2. Then from this, what I can write, x equals to minus 2y minus 3z, but y is k2, z is k1, so minus 2k2 minus 3k1. Therefore xyz equals to, I am writing this as linear combination, so xyz. So from this I will get k1, if you take out outside, minus 301 and k2. Here k1 and k2 are simultaneously, they are not equals to 0. Right? If they are equals to 0 simultaneously, we left over with 0 eigenvector, which is not possible. Therefore, compulsory k1 and k2 must be not equals to 0 simultaneously. Okay. So, if I want one eigenvector here, I will choose k1 is 1 and k2 is 0, so that I will get one eigenvector. Next, I will select k1 is 0 and k2 equals to 1. I will get the other eigenvector. Next, I am calculating the third eigenvector lambda equals to 14. For eigenvalue lambda equals to 14. So put lambda equal to 14 in the system 1. So in this system we are substituting that one, so that I got this one. So reduce this matrix to upper triangular matrix by using the transformations. So here I applied the row transformation. So what is this row transformation is, R2 is, what I am doing is, so I am multiplying this with 13 and I am multiplying this first row with 2 and I am adding those 2. Therefore, I will get here 0. So these are the two row transformations which we applied for second row and third row, and we got this matrix. Next, if you look at this one, now I have to make this entry 84 as 0. So for that, what I am doing is I am multiplying this third row with 126 and second row with 84, and I am adding both. So I got this one. Now from this I can write, see here, from this I can write minus 126y plus 84z equals to 0. That is one equation. Another equation is minus 13x plus 2y plus 3z. So here I am choosing z equals to k. So from that I will get y equals to 2k by 3, and if I substitute that in the equation minus 13x plus 2y plus 3z, I will get x. So those equations are not written here because in the previous sections we done already this type of problems. That's why directly I am taking the value of x, y, z. So now the third eigenvector what we got is this one. So k is not equals to 0, which is a scalar. So if I want the third eigenvector, simply to avoid fractions, I will select here k is 3. Therefore, I will get 1, 2, 3 is my eigenvectors. Therefore, the eigenvectors corresponding to the eigenvalues is, these are the 3 eigenvectors we got. Once you got the eigenvectors, what you have to do is, in the previous sessions we have seen, directly we are constructing the model matrix P by taking these 3 column vectors as first column, second column and third column, and we are constructing the model matrix. But here, because we want the orthogonal diagonalization, first of all these 3 vectors must be orthogonal to each other. So let us check x1, x2 whether these two are orthogonal or not. Clearly minus 3 into minus 2 is plus 6, 0 into 1 is 0, 1 into 0 is 0. So this is 6, which clearly it is not equals to 0. If it is equals to 0, no problem. Next, x2, x3, if you check it, clearly it is equals to 0. Next, if I check it, x1 and x3, clearly it is 0. So only the problem is coming with x1 and x2. Therefore, what I am doing is, here I want to change this x1 so that it must be orthogonal with the remaining 2 vectors. So I am constructing this new x1. So I am taking x1 is ABC and the remaining x2 and x3 as it is. So now x1 must be orthogonal with x2, means what I will get is minus 2a plus b equals to 0. Similarly, x1 must be orthogonal with x3, means I will get a plus b plus 3c equals to 0. So here I am choosing b equals to k. If I choose b equals to k here, what I will get is a equals to k by 2. So I will substitute that b and a in this. I will get c equals to this one. Therefore, my new vector x1 is ABC, which is this one, k by 6 times 3, 6 minus 5. So if I select k is here 6, I will get 3, 6 minus 5 is the new eigenvector x1. Now these 3 vectors are pairwise orthogonal. So now there is no problem. Once the vectors are pairwise orthogonal, what you have to do is you have to normalize them. So I calculated the norm of x1, that is square root of 3 square plus 6 square plus minus 5 whole square. So it becomes root 70. Next, norm of x2, minus 2 square plus 1 square plus 0 square is root 5. Next, norm of x3, root 1 square plus 2 square plus 3 square, root 14. Now I am going to construct the normalized model matrix. So the normalized model matrix P equals to, earlier we are constructing just model matrix. Now it is normalized model matrix. So x1 by its norm, I have to divide with this norm. So 3 by root 70, 6 by root 70 minus 5 by root 70. Similarly, x2 I have to divide with its norm. So minus 2 by root 5, 1 by root 5, 0. Similarly, the third one, x3, 1 by root 14, 2 by root 14 and 3 by root 14. So now we got P here. Once you got P, next we want P inverse. For P inverse, there is no need to worry about, because the matrix P, whatever we got this one after normalizing, this definitely it will behave it as an orthogonal matrix. Once it is an orthogonal matrix, therefore calculating its inverse is nothing but writing its transpose, because what is orthogonal matrix? A matrix A is said to be orthogonal whenever A transpose equals to I. That means A transpose is nothing but A inverse there. Similarly here, this P, what is this P? Normalized model matrix, which is nothing but an orthogonal matrix. Therefore, to calculate P inverse, it is enough just you take the transpose of this matrix. So we done the transpose of this one. Now I want to diagonalize this matrix. So D equals to, earlier we are writing P inverse AP, the formula. Now instead of P inverse, I have to write P transpose, because this P is a orthogonal matrix. So I substituted P transpose here. A is the given matrix, P is the normalized model matrix. So after multiplying these three, I got D equals to 0, 0, 0, 0, 0, 0, 0, 0, 14. So it is a diagonal matrix. And if you look at the leading diagonal here, very clearly, this leading diagonal is having the entries 0, 0, 14. So with these are nothing but the eigenvalues of our given matrix A. See here 0, 0, 14. So this is the procedure of diagonalizing, orthogonal diagonalization of the given symmetric matrix. So the procedure is very simple. Once again, I am summarizing this one. Okay, so they will supply a symmetric matrix to you, right? What you have to do is you have to calculate the eigenvalues first. Next, calculate the corresponding eigenvectors. So you will get the corresponding eigenvectors, 3 eigenvalues, and you will get the corresponding 3 eigenvectors like this. Once you got the eigenvectors, what you have to do is, before normalizing them, first check it whether they are pairwise orthogonal or not. If they are pairwise orthogonal, directly you can calculate their norms and divide each vector with its norm to construct the normalized model matrix. Suppose if they are not pairwise orthogonal, right, then you have to make them as orthogonal. And that means you have to calculate, you have to construct orthogonal matrix. You have to construct orthogonal matrix, right? So that means you have to check it whether they are pairwise orthogonal or not. So to check that one, that this is the procedure you have to adopt. So whichever is failed, we have to construct that one. So in this case, x1 is failed. Therefore, we selected x1 is ABC, x2 is this, and x3 is this one, right? We got x1. Once you got x1, x2, x3, so normalize them, then construct the model matrix P. Next, P inverse. Here P inverse is very easy because P is an orthogonal matrix, so its transpose is nothing but its inverse. Okay, so then P transpose AP, just product of 3, and finally we'll get the diagonal matrix. So this is the simple procedure. Okay, so I am Srikanth Reddy. Thanks for watching. I will see you in the next video.